As systems manage higher volumes of complex data, developers increasingly turn to index data structures to enhance performance in locating a given data object. Used properly, indexes can boost speed logarithmically beyond that of a linear data search. However, when indexing is contemplated, the first and often the only index to be considered is likely to be the B tree, as Chris just mentioned. Out of all the indexes that can order records in database management systems, only B trees are offered universally. And often they're the only index offered, and there's no denying B trees' efficiency for basic database search operations like exact match, prefix, and range searches. But these plain vanilla indexes are often a poor fit for certain data and access patterns, such as IP routing, geospatial searching, and in-memory database systems. Therefore, it pays for a programmer to understand a wider variety of indexes that may at first glance appear more exotic. Diverse index types enable important design trade-offs involving search performance, memory consumption, and update performance, and some indexes offer distinct advantages for certain application categories. This presentation is going to examine less well-known indexes that can be a good fit for certain application needs. The B tree is the most popular data structure used in database and file systems and provides efficient general-purpose lookup and sorted retrieval of entries for a large volume of data. We'll look at R trees for geospatial indexing, which is common in GPS and navigation type systems. We'll examine the Patricia tree for router and telephone directory searches. This is also known as a longest prefix match index. T trees are appropriate for all in-memory data storage and access. Whereas the design goal of a B tree is to minimize I/O, the design goal of a T tree is to minimize memory use. Hash tables can quickly locate a single unique index entry. Hash indexes can be faster and use less memory than either of the types of tree indexes. And then custom indexes are B trees that allow the application to define the collating sequence or the sort order of the entries rather than defaulting to a simple lexicographical or numerical sorting. And we'll look at a couple of examples of where being able to control that comparison function could be useful. A hash table is one of the most efficient ways to perform key value mapping. The idea of the hash table is to calculate some integer number that we call the hash code from the original key value. Then this number is used as an index in the array, in other words, an index into the hash table. Since the same hash code may correspond to different keys, there are conflicts, which we usually refer to as collisions. A hash table's efficiency greatly depends on the quality of its hash function. If the hash function is able to minimize the number of collisions, then a lookup in the hash table is very efficient and requires just a few checks. On the other hand, a bad hash function can ruin performance. For example, consider a simple dictionary with a string key value. Assume that the hash function is defined to be an exclusive OR of all bytes of the string. And then ask yourself, how good is that function? Well, unfortunately, it's not very good. It can yield only 256 possible values of the hash code. Thus, the hash of 1 million strings would create, on average, 4,000 conflicts. Conflicts are often resolved by maintaining what's called a collision chain, which is a linked list of elements with the same hash value. In order to locate a specific element, then the algorithm has to perform a linear search in that list of 4,000 elements, which, of course, is very inefficient. Unfortunately, it's not really possible to define one ideal hash function for all data types and for all distributions of data values. So to mitigate this, database systems will often have multiple hash functions. Another consideration is the hash table size. The hash code is used as an index into the hash table. But what's the size of that hash table? The calculated hash code can be very large, and it might not be possible to create an array of that size. So to compensate, the hash code is often the remainder after dividing the hash code value by the hash table size. But by doing so, the algorithm creates collisions, and so then measures have to be taken to minimize the number of collisions. If the number of elements is unknown, then the hash should either add more and more elements to the collision chains, which makes searches less efficient, or reallocate the table dynamically from time to time, which has its own performance implications. There are two general approaches to resolving collisions. They're called open addressing and chaining. With open addressing, each entry in the hash table holds a single value. With chaining, each entry in the hash table is the head of a chain of pointers to values that hashed to that hash code. So let's look at open addressing first. With this method, a hash collision is resolved by searching through alternate locations in the array, which is called the probe sequence, until either the target record is found in the case of a search, or an unused array slot is found, which in the case of a search means that the value was not found, or in the case of an insert, is an available slot to store the value. The well-known probe sequences include linear probing, in which the interval between probes is fixed, usually at 1, quadratic probing, in which the interval between probes increases linearly, hence the indices are described by a quadratic function, and double hashing, in which the interval between probes is fixed for each record, but is computed by yet another hash function. The main trade-offs between these methods are that linear probing has the best cache performance, but is the most sensitive to a phenomenon called clustering that we'll discuss here in a few minutes. Double hashing has the poorest cache performance, but exhibits virtually no clustering, and quadratic probing falls somewhere in between both areas. On another note, the performance of an open addressing hash table depends on the load factor, or the proportion of the slots in the array that are used. As the load factor increases towards 100%, the number of probes that might be required to find or insert a given key rises dramatically. Once the table becomes full, then probing algorithms might even fail to terminate. They just won't find any empty slots. Even with good hash functions, load factors are normally limited to 80%. A poor hash function can exhibit poor performance even at very low load factors by generating significant clustering. All right, let's take a closer look at linear probing. In this algorithm, if a location is occupied, the logic simply iterates through the hash table elements sequentially until an open location is found. In our example, the hash function is the key value modulus 11. Remember, we said the hash code is usually the remainder after dividing the hash code by the table size. So if the hash code turns out to be larger than the table size, then we're going to take the hash code, divide it by the table size, and use the remainder as the index into the hash table. So that you can see the sequence of steps to store some key values here. So the key value 20 modulus the hash table size 11 gives us a value of 9. So we store the value 20 in bucket number 9. And then 13 modulus 11 is 2, but 2 is already occupied by the previous value, so we just add 1 to it using linear probing, and we store the value 13 in bucket number 3. Likewise, 24 modulus 11 is also 2, but again 2 is occupied, so the linear probing looks at 3, which is already occupied, and goes down the line until it finds an empty bucket, in this case bucket number 5. So exploring that concept of clustering. So imagine that the colored squares in the 10-element table at right indicate values in a hash table that have already been filled. Now assume that the next value will, with equal probability, be any of the 10 values. So what's the probability that each of the free squares will be filled? Well, since both positions 1 and 2, counting from 0, are filled, any value that maps to these locations must go to the next free location, which is 3. So the probability that square 3 will be filled is 3 out of 10, while the probability that square 0 will be filled is only 1 out of 10. So that phenomenon, where the larger a block of filled cells becomes, the more likely it is to become larger, is called clustering. Incidentally, a similar phenomenon explains why groups of cars get larger and larger on the road. As I said earlier, quadratic probing exhibits less clustering than linear probing and has better cache performance than double hashing. In our example, the hash function is again the key value modulus the hash table size, which is 11. So take a moment to go through the calculation of the hash codes. Note that in the case of the value 9, the last two probes result in hash codes that are larger than the table size, so the hash code is reduced to the remainder of the hash code divided by the table size. Double hashing exhibits the least clustering, but has the worst cache performance. In this example, the first hash function is the value modulus 11, as in the previous examples, and then to resolve collisions, the second hash function is 7 minus the value modulus 7, which is multiplied by 2, 3, 4, and so on when further probes are required. So let's look at how the hash code for the value 91 is arrived at. So 91 modulus 11 equals 3, which is occupied. So we go to the second hash function, 91 modulus 7 equals 0, 7 minus 0 equals 7, and 3 plus 7 equals 10, which is also occupied. So we take 2 times the second hash function, which gives us 14, and we add it to the result of the first hash function, 3, to get 17. But 17 is larger than the hash table size, so we take its remainder after dividing by the hash table size, which gives us the hash code 6. So the value 91 is stored in bucket number 6. And again, I'll give you a moment here to study the sequence of probes that are illustrated on this screen. Another more straightforward means to address collisions is chaining. So whereas in open addressing, each location of the hash table holds only one item, we can instead define a hash table in which each location is the head of a chain. This is called separate chaining. The chain is a linked list of the data objects or the values that hashed to that location. So now instead of doing probing, we're just going to chain the values that had collisions to the same bucket. Thus, the hash table that uses buckets is really a combination of an array and a linked list. Each element in the array, or the hash table, is a header for a linked list. All the elements that hash to the same location will be stored in that list. Each operation on the hash table then divides into 2 steps. First, the element is hashed, and the remainder taken after dividing by the table size, and that yields the table index. Next, the entry is added to the linked list, indicated by the table index in the case of an insert, or the chain is walked to find the specific value in the case of a search. The main advantage of hash tables is that fast search times requiring few checks, and ideally just one check, can be almost independent of the number of elements in a hash table. In other words, doing a lookup into a hash table of size 100 is just about the same as doing a hash lookup into a hash table of size 1 million. But the price for that advantage is high. First, it requires choosing a good hash function, which is non-trivial, especially since defining an ideal hash function for all types of data is really impossible. And secondly, it requires maintaining a larger hash table or a larger array than the amount of data being managed. Again, remember, we want to keep our load factor below 80%, so we need a larger table than the actual number of elements that we want to store in the table. So if there's several million elements, then the hash table size could be several megabytes in order to avoid walking long collision chains or having very long probe sequences. And that's not always possible. And one of the most crucial hash table limitations is that it doesn't preserve key order. So if range queries are needed, for example, select persons with an age greater than 30 or with a salary between some minimum and some maximum, then a hash table isn't going to be able to help you optimize that query. And for that reason, database system indexes are usually implemented with B-trees, with hash tables available only if they're explicitly requested. Hash tables should be used for auto-generated identifiers where the order isn't important for the application, but are frequently used and require fast access time, for example, for joins. So, for example, if your database supports a serial or a sequence data type in ExtremeDB, we call it an auto ID. That's a great candidate for a hash index. It's typically just used for fast lookups and for joins. You don't care about the order. Hash table interfaces, therefore, usually only include put and get methods to add, find, and replace elements in a hash table. It might be possible to iterate through all the hash table entries, but the order is going to be unpredictable.